Okay, so yesterday we proved that for any fusion category over the complex field, the Frobenius parent dimension divides the categorical dimension in the algebraic sense, and in fact, the ratio is less than or equal to 1, which is surprising if you have just integral intuition, but that's okay. And we finish by stating that, in fact, this kind of the fact that this ratio equal to the square of a dimension of an object extend to the formal category, in fact, due to Ostrik. Anyway, so we are in the section about pseudo-unitary fusion category, so we did not yet define. We just prepare. So pseudo-unitary will be defined as this equal this. So let me just first state remark. So the square norm, so we already mentioned that the square norm is less than or equal to the square of the Frobenius parent dimension. So if the categorical dimension equals the Frobenius parent dimension, then so this implies that the square norm equal the square of the Frobenius parent dimension for all simple objects. And in fact, so as I said, the pseudo-unitary will be precisely when we have such an equality. The fusion category C over the complex field is called pseudo-unitary. Pseudo-unitary if the categorical dimension equals the Frobenius parent dimension. Frobenius parent dimension of C. Or equivalently, if the square norm of any simple object equal to the square of the Frobenius parent dimension. But be careful. In fact, warning. It is not true in general that dim x equal fp dim x for all x, but we will prove the existence of a spherical structure, of a canonical spherical structure. Phi. So here I put phi before the saying that it's a spherical structure, but we will state this theorem soon, so it doesn't matter. So there exists a canonical spherical structure such that this equality holds for all simple objects. So, pseudo-unitary, it's only that for all simple objects. You don't have that in general, but you can find a canonical spherical structure such that you have that. So it's a bit you have to be careful, in fact. You have to choose a good canonical spherical structure such that you have that. Otherwise, you have only that. Okay. Okay. So, of course, example of pseudo-unitary fusion category are given by finite group. Let G be a finite group, then rep G is pseudo-unitary. Okay. But more generally, we will prove soon, maybe next week, we will prove soon that any weakly integral there will soon be a section about weakly integral fusion category, which mean fusion category C, which mean the categorical dimension is an integer. In fact, is pseudo-unitary. So it is pseudo-unitary, so the categorical dimension is the Frobenius dimension, so it's an integer here. And we will see also, and we will also see that dimension x squared is an integer for all x simple objects. So, so what is the point of this remark? The first point of this remark is to provide a huge class of example of pseudo-unitary fusion category. In fact, all the weakly integral. So as long as the categorical dimension is an integer, we will prove soon that it's always pseudo-unitary. For example, this one is integral, so it's pseudo-unitary. The same for, of course, for any I don't know, finite dimensional semi-simple of algebra over the complex field. It is integral, so it is as for this one, it is pseudo-unitary. So you have plenty of examples of pseudo-unitary fusion category. In fact, we will see how to say. It's quite hard to define a fusion category which is not without pseudo-unitary category reflection, or at least without pseudo-unitary Galois conjugate. So let me explain a bit how to define a non-pseudo-unitary fusion category, but using Galois conjugate. And then I will just state a result about a fusion category which is not Grothendieck equivalent to a pseudo-unit due to Andrew Chopiré. But before that, so let me quickly state. So we will see later also that any fusion category C admit a conjugate, Galois conjugate, admit Galois conjugate, admit Galois conjugate. Let me call C sigma like that, with the categorical dimension of C sigma equal to sigma of the categorical dimension of C, with sigma an automorphism of the field, of the complex field. In fact, an automorphism of, let me call that, an automorphism of the algebraic number. We will briefly state that in a few more details later, but I just wanted to provide example and counterexample of about pseudo-unitary. It may be relevant to talk about that here. So it follows let me say proposition. Let C be so what? Be a non-weakly integral fusion category. So you take a fusion category which is not weakly integral. So which means that the categorical dimension of C is not an integer. Then it admits a Galois conjugate C sigma, which is not pseudo-unitary. So Galois conjugate, I will state soon what does it mean, but in fact, you take this field automorphism and you apply it to all the constant structure of the category. We proved in the previous proposition that some few sessions ago that all the fusion category can be defined on the algebraic field. So you can apply that to all the constant appearing in this category, and you get that. So that may require a bit more details to explain in what sense it's well defined. It provides also a fusion category, but just assume that we just need this property, that the categorical dimension of the conjugate is a conjugate of the dimension under sigma. So if you have a non-weakly integral fusion category, it admits a non-pseudo-unitary conjugate. So proof. So suppose so C is not weakly integral. Okay, so you need to suppose that. So if, so by contradiction, if the conjugate of C is pseudo-unitary for all possible conjugates, then define the deux lignes tensor product over all the sigma, so all the possible sigma providing conjugate of dim-C. So the categorical dimension of C is an algebraic integer, so it has finitely many Galois conjugates, and you only consider the conjugate, the conjugation coming from the conjugate of dim-C. Okay, and you consider the deux-lignes tensor product of all such conjugates. So let me just mention here that this idea to consider this, in fact, come from a discussion with Yilong Wang. So I don't know if this idea comes from him or if it was mentioned before in the literature, but at least I got this idea from him. I don't know from him he got this idea, but I wanted to mention that. So you get, you consider this deux-lignes product like that. So if they are all pseudo-unitary, so the deux-lignes product will be pseudo-unitary, is also pseudo-unitary. Of dimension with so equal to the product of the conjugate of Frobenius parent dimension of C. Okay, in particular, C itself is pseudo-unitary because you just take the trivial conjugate. They are all assumed to be pseudo-unitary. But this is the algebraic norm of the Frobenius parent dimension of C. The algebraic norm. Algebraic norm. So the constant term of the minimal polynomial. For the algebraic number fp dim of C. So it is an integer. This is an integer. So this is weakly integral. Weakly integral. Contradiction with C. C is a fusion subcategory of C tilde. Non-weakly integral fusion subcategory. Why contradiction? Because then the simple object of C is a subset of up to isomorphism of the simple object of C tilde, but for all x in C tilde, by dimension x squared is an integer, and there exists x in C for which it is not. So it's a contradiction. Remember that weakly integral here imply that every dimension of simple object is an integer or a square root of integer. So every simple object here has for dimension a square root of an integer, but it is not true here. But it's a subset, so it's a contradiction. So the hypothesis was false. There must exist a conjugate which is not pseudo-unitary. Okay. So that's quite nice. In fact, you see how we use Galois theory. So the notion of Galois theory in this theory is fusion tensor category is really fundamental. The notion of Drinfeld center is fundamental. Modular category is fundamental. The Galois theory is fundamental. Very important. Okay. Okay, so that's okay for this proposition. Now, so you get at least plenty of examples of pseudo-unitary fusion category, all that as long as it is weakly integral, it's pseudo-unitary, we will see soon, and plenty of examples which are not pseudo-unitary. So conjugate of a non-weakly integral. But the previous example is a bit cheating. Wait. But so such conjugate in fact in the next session we will call it like that, we will denote it like that, but for here I wanted to write it like that. It's okay. Such conjugate has the same Grothendieck ring because the fusion data is given by integer, and integer are invariant by Galois conjugation. So the same Grothendieck ring, because the fusion data is made of integer only. So invariant by conjugation, Galois conjugation. But so it's a bit cheated. In fact, this non-pseudo-unitary category are always coming from such construction are conjugate to a pseudo-unitary one. In fact, they are Grothendieck equivalent to a pseudo-unitary one. What will be interesting is to find a fusion category which is not Grothendieck equivalent to a pseudo-unitary one. And at the time of the book was written, it was an open problem, which is solved now by Andrew Chopiré. So at the time of the book was written, it was open whether there is a Grothendieck, there is a let me say like that, there is a Grothendieck ring. So Grothendieck ring without pseudo-unitary categorification. So I am talking about, when I say Grothendieck ring in this section, I am talking about the Grothendieck ring of a fusion category. So I am talking about a fusion ring with a categorification, but not a pseudo-unitary categorification. So I am saying that it was an open problem whether there exists a fusion ring which is not Grothendieck equivalent to a pseudo-unitary fusion category. So let me state it like that. Whether there is a fusion category, whether there is a fusion category which is not Grothendieck equivalent, so same Grothendieck ring, to a pseudo-unitary one. Pseudo-unitary one. But this was solved so by Andrew Chopiré, which is he was a PhD student of Viktor Ostrik. So I found an example, or published an example, which is in fact, which is simple and modular. Simple modular of rank 6 and multiplicity 2, if I am not mistaken. So it was not so far. It was not so far. In fact, rank 6 multiplicity 2 can be found by brute force. So by brute force, you can find such a category. Because you can classify all the possible fusion ring of small rank, small multiplicity. The work by Just Verkleyen. They provide in a classification of small rank, small multiplicity fusion ring, and so you can try to see which one admits a modular categorification, and you can find at least this example like that, and then the proof whether it admits no pseudo-unitary categorification. I'm not sure whether it's easy to do. Anyway, automatically. Okay, so that's okay for this list of possible example and counterexample about pseudo-unitary up to conjugate or up to Grothendieck equivalence. Okay, so let me explain quickly why we are talking about pseudo-unitary. In fact, pseudo-unitary here means that it's almost unitary. So remark. So I don't want to state it as a definition because I will not provide the full definition. So if the field is complex, the fusion category is called unitary. If there are some property I will write briefly, and then, in fact, unitary fusion categories are pseudo-unitary. And the converse is an open problem. At least the existence of a pseudo-unitary structure, of a unitary structure for any pseudo-unitary category is an open problem, a very, very exciting problem. Okay, so it's called unitary if it is a C-star fusion category, which means that the home space is as a structure of linear product space over C together with additional C-star axioms, and that I will not write. In fact, it is not written in the book also. So if you know what is a C-star algebra or something like that, you are trying to make some axiom for a fusion category looking like what you have for C-star algebra. This gives the definition. The point here is that so example. So again, if G is a finite group, then rep G is unitary. Now, we see this that do not extend to, so warning, that do not extend it does not extend yeah, how to say no, easily or a priori. No. Let me just say we don't know whether it is true for any finite dimensional of semi-simple of algebra over the complex field. What we know is that if H, but it's true, yeah, let me state like that. But it is true if such H is a C star of algebra, which means that the co-multiplication and the co-unit deal with the star structure. Some sense. Okay. And so this is one example, another example. So third example, the fusion category coming from subfactor theory. Subfactor theory are unitary also. And in fact, so let me write it like that. One first kind of example, two second kind of example, and three third kind of example. In fact, the second kind of example is, so two is included, one, the class of example one is included in the class of example two, and the class of example two is included in the class of example three. In fact, you can see C star of algebra as subfactor. In fact, two correspond to depth 2, irreducible, finite index subfactor. There is a famous correspondence. I already mentioned that several times. And a proposition without proof here, proposition, as I said, unitary implies pseudo-unitary. So you see, pseudo-unitary is a purely algebraic notion. Categorical dimension equal the Frobisher dimension. Unitary, there is a bit of a piece of analysis. You need inner product space and you need some C star axiom. So it's but we don't know, in fact, whether the other way can go the other way. More precisely, it's an open problem. So the proof here is skipped. It's an open problem, a very famous open problem, in fact, very interesting. So let C be a pseudo-unitary category. Is there a unitary structure on C? Or, if you prefer, is there a pseudo-unitary category without unitary structure? If you want to state this negatively. And as I said here, you can reformulate what I said here in orange as follows. It's even open for finite dimensional semi-simple of algebra over C. So what is open here is the existence of a star structure compatible with co-multiplication and co-unit over C. So if, so I guess what I should say that Webpage because H unitary imply H sister of algebra. Something like that. Anyway. So it's a famous open problem in of algebra theory, whether any finite dimensional semi-simple of algebra over C admit a star structure. So all the example we know admit the star structure, this unit. Okay, so okay, so that's okay. That's nice. Nice kind of problem. Okay, so we mentioned this canonical spherical structure before. I guess here somewhere. Where is it? Here, canonical spherical structure. Now it is the time to provide more details about such canonical spherical structure, for which, in fact, you have that. Okay. So this is the point of this new subsection, canonical spherical structure. In the pseudo-unitary case, not in general. In general, it's an open problem. The existence of a spherical or even a pivotal structure in general. Okay. So we start from a general fusion category over the complex field. And so let me recall what we stated as Radford isomorphism for force dual. So recall Radford's isomorphism for force dual. So there is the existence of a natural tensor isomorphism, and tensor is very important. Isomorphism G. So again, given by collection, such that G is a collection of isomorphism between X and the force dual, between identity and force dual functor. So we will start with that. Now we will make the pause. So, okay, so natural tensor isomorphism between the identity functor and the force dual functor, which what was called the Radford isomorphism for force dual. Okay, so the point here, so before talking about pseudo-unitary, so wait. In fact, we will mention a quite long few details about the square root of such tensor isomorphism. So in fact, the square root of that, we will explain the meaning of that. It will not be a tensor isomorphism. If it is a tensor, if it is tensor, then we will get this expected canonical spherical structure, but it's not tensor in general. But we will see that we can find a tensor one in the pseudo-unitary case. Okay, so we will define a square root of G. So S square equal G here, which means a natural isomorphism. A natural isomorphism, which is not necessarily tensor, maybe not tensor. So A equal AX with AX collection of isomorphism between the identity, so isomorphism between the identity and the double dual functor. So recall that for a fusion category, for fusion category, the double dual of X is isomorphic to X. More general than fusion category, but semi-simple finite tensor category. No, semi-simple. I don't remember. Semi-simple category. At least for fusion, it's okay. So okay. So this isomorphism Gx is C-linear. That's okay. And the fusion category is semi-simple. So we only need to consider Gx with X simple. Then Gx is a scalar. Can be identified with a scalar because by Schur lemma yeah, anyway. Okay. Okay. So it's a scalar. So admit a scalar square root ax square equal Gx in the complex field. Such scalar ax define the natural isomorphism ax. So we also call ax like that. Such that ax double star composed with ax is Gx. Okay, so as a morphism. Ax star, ax square equal gx as a scalar, but as a morphism, we need to, because ax go from x to x double star. Then you have to go from x double star to x 4 star. So you really have a morphism for x to x 4 star. Okay. So you get, so maybe you have something to check here that really define a natural isomorphism between the identity and the W value. But up to that, you get such a natural isomorphism, which is not necessarily tensor. We will see the condition making it tensor. So as I said, it's not tensor. A equal ax is not tensor in general, which means that ax tensor ay is different from ax tensor y. Now, ax tensor ay is a morphism from x tensor y to x double star to y double star. This is isomorphic to the direct sum with multiplicities. So simple object in the V X, so multiplicity space, tensor V, and this is isomorphic to. So we can write here, it's more convenient to write V double star, but it's just a change of variable. There is nothing complicated here. X double star, tensor Y double star for multiplicity space, V double star. Okay. So you have such a morphism. So you see this morphism decomposed into a morphism for each component like that. So ax tensor ay decompose into linear isomorphism. So if you prefer, you can say invertible matrix. Denoted like that, B, X, Y, V from the Hom space V X tensor. Like that. Double star, tensor Y double star. By short lemma, in fact, you see everything involved. If you have two non-isomorphic here, it will be 0. So you only need to care about when this is isomorphic to this. So you only need to care about the multiplicity space. So you have, if you prefer, a matrix between this space and this space, which is exactly what we wrote here. And in fact, you can how to say? In fact, this space, this Hom space, is naturally identified to the Hom space Vx via natural adjunction isomorphism. So you can, in fact, identify both. You can identify this one. They are isomorphic, but they are, in fact, naturally isomorphic. So at the categorical level, you can safely identify these two. So you can just consider this as a matrix between this space and itself. So we can consider Bx as in here to such identification. Okay, so that's okay. So we have this list of matrices. Now, what's the difference with this? In fact, this, you see, so as I said, so you have Ax tensor Y is equal to the direct sum of V simple of this such matrix, not this one. So I'm going too quickly. So this is like that. This matrix tensor AV. Okay. So this is the decomposition of AX tensor AY. Whereas the A of X tensor Y is the direct sum V in C of identity of the space tensor AV. So to have this equal this, you need this to be the identity matrix. And this equality is easy to see because this is so you decompose AX tensor Y, and at least A is not tensor, but it's linear. It's C-linear. So it should be okay. So A equal AX is tensor, which means pivotal, in other words, if and only if Bxyv equal identity of the space for all xyv simple object. Okay. So this is the precise way to say when natural isomorphism between the identity and the double dual is tensor, is pivotal. You need this component to be identities. Now we considered, in fact, A as a square root of a tensor, of the tensor G. So now AX double star composed with AX is GX, which is tensor. So GX is tensor. So if you apply what we did before, when you decompose GX tensor Y, you get identity for GX tensor Y. So then you will prove, we will see that in fact, for this such a square root, we have the square of this matrix to be identity. So AX double star composed with AX tensor AY double star composed with AY, which is equal to, so So it's coming from G. So of identity AV double star composed with AV because G is tensor. Like that. But you can develop it in another way. It's equal to AX double star tensor AY double star composed with AX tensor AY, which is equal to the direct sum over the V double star of B, V double star, Y double star, V double star, tensor A, V double star, composed with sum of A, X, Y, V, tensor A, V. But, okay. So it's equal to the direct sum over V of VB, like that. Compose B, X, Y, B, tensor AV star AV. Okay. Now, so then you have that. Right? You have that equal that. Then, thus, under previous identification, so identification here, we identify this space with this space naturally. So we identify this matrix with this matrix. So under previous identification, we get that bxyv square equal identity for all xyv simple objects. Okay. So you can do that in general. Okay. So now, now consider. Let me remove that. Consider the dimension of the home space. N, X, Y, V dimension over the complex field here of the home space between V, X, tensor Y, which is the trace of the identity of its home space, and it's an integer, and consider the trace of the matrix BXY, BXYV. So TXYV to be the trace of the matrix BXYV decomposing, coming from the decomposition here. Okay. But BXYV square is identity. So the eigenvalue of bxyv are solution of x squared equal 1. So they are plus or minus 1. They are in minus 1, 1. The eigenvalue. So its trace txyv as the sum of eigenvalue. Its eigenvalue is a sum of the form sum from I equal 1 to nxyv of epsilon I with epsilon I in minus 1, 1. Okay. So it's a sum of nxyv plus or minus 1. So the module, no, how to say it? The norm. Anyway, this sum, so the absolute value of nxyv is, of course, less than nxyv, because you have a sum of plus or minus 1. So it is between minus nxyv to nxyv. This sum is in between. So in particular, its absolute value is less than 1. And so, moreover, the equality hold if and only if yi equal 1 for all I. But in fact, wait. What I mean by equality. So let me just say it like that. And the equality txyv hold if and only if bxyv equal identity. Yeah, sure. You have because every so if you have equality, all the epsilon y should be 1, and the identity is central. So if all the eigenvalues are 1, then it must be the identity. Yeah. Yeah, I guess. Okay. So if and only if epsilon I equal 1 for all I, if and only if bxyv equal identity. if and only if A equal AX is pivotal. So it's a tensor structure, so pivotal by definition, which is what exactly the equality between this and this. Identity is central. So you need the identity to be central. You need to say that. Then every conjugate of the identity is the identity. So if all the eigenvalues are 1, then it must be the identity. And it's yeah, it is an isomorphism also. And BXYV invertible should be enough. I hope it's enough. Identity central, this is invertible. Do you need something else to get only the identity? I hope so. Otherwise, it's just an algebra exercise. Okay. Okay. So the equality hold, this equality hold between this trace, these two traces, if only if we have the pivotal structure. Okay, so now we are not yet done about, we are not yet ready to come to pseudo-unitary case. So if so let dx be the trace of ax. Let us apply the trace to ax tensor a1 equals sum bxyv tensor av. So I have a doubt here. Is it enough? We should also prove that this matrix is self-adjoint, or is what? It should be diagonalizable, in fact. What if it is not diagonalizable? If it is diagonalizable, then the fact that the identity is central is enough. But if it is not diagonalizable, so we should prove that it is self-adjoint or self-dual, or self-adjoint or normal, or I don't know. May need. May need more. Plus more. When I say plus more, I need, should we have more property of this matrix to get that? Anyway, so it's a small question mark here. Okay, so you have this decomposition. So you apply the trace. You apply the trace here. You get dx dy equals the sum for the sample txyv dv. Okay, so this is okay. So, but the exercise. So here it's stated without proof, but I was a bit confused. Exercise show that the square norm of x is equal to the absolute value of the square absolute value of dx. So of course, the square norm is defined using a natural isomorphism between the identity and the double dual functor, and it is independent of the choice. But we have a formula, I don't remember. So for all x simple, C section 721, equation 770. So we see here that the definition of square norm is independent of the choice. So you have a formula involving ax, but why it should be equal to that? There is a small details I'm missing, so I put this as an exercise here. In fact, it is fundamental. We really need this equality, so it should be trivial. But I was not able to fill this gap quickly during my preparation, so I put that as an exercise. In fact, it was not explained in the book also. Okay, so now we can state the expected proposition. Which will use the preparation before in the proof. A pseudo-unitary fusion category admit a unique, in fact I did not prove unique, spherical structure AX such that dx equals the Frobenius parent dimension of x for all simple objects. Okay, so this is what we want. So proof. So I guess I will have no time to finish the proof today, but I will start. Proof. Let C be a pseudo-unitary fusion category. Let Gx and Ax the square root as before. Tensor isomorphism. Ax from x to x double star its square root as before. Okay. The idea to get the expected spherical structure is to twist Gx. the idea here is to twist gx such that dx equals the trace of x positive. Okay, so by the pseudo-unitary assumption, you know the square root, the square norm of x is the square of the Frobenius power dimension of x. By pseudo-unitary assumption, square norm of x is Frobenius power dimension of x squared. For x is the simple object. But square norm of x is the square of the absolute value of dx as the exercise state here. So the absolute value of dx is the Frobenius parent dimension of x. Now you can apply the dimension equation. Frobenius parent dimension of x times Frobenius parent dimension of y is equal to, so as written before, just the absolute value of dx dy, which is the sum over the simple object of t, so absolute value t xyz xyv dv, which is less than the sum over v, absolute value of txyv, absolute value of dv, which is less than the sum over v of n xyv f edim of v by because we proved, because we saw a few minutes ago that we had that, and this equal this equal this, which is equal to Frobenius parent dimension of x times Frobenius parent dimension of y. So you have a chain of inequality between two equal numbers. So every intermediate should be equal. So the equality holds. And absolute value of tx by positivity, in fact, must be nxyv. In other words, you can say that txyv is plus or minus nxyv because nxyv because txyv is equal to the sum of epsilon I equal 1 to nxyv epsilon I minus 1 1. So if it has the same absolute value, it must be one of the two extreme for such sum. So minus or plus nxyv. Okay. And here there is another exercise, which is not, another point in the proof, which is not detailed, that I was not able to quickly find the details, to show or to deduce that dx dy over dv is real. The real number is real if nxyv is different from 0. That during my preparation this morning, I was not able to understand how to prove that. So I put it as an exercise. Okay. So as long as this exercise is proved, then if it is real, then its square is positive. Is positive when this is non-zero, which means that V is a component of X tensor Y. If V is a component of X tensor Y. Okay. Okay, so yeah, it remains too much thing. So I will. So we will finish the proof next time. So we will finish the proof next time. So let me end the session here.